Shalom and welcome to this live stream from Me Israel for Fred. Me Israel for Fred is a pro-Israel organization working in Norway since the 1970s, and in recent years we have also started in Sweden, Denmark and Iceland. This is a unique live stream. It will all be in English. It's not every day that an Israeli scientist are awarded with prizes from Norway, but it happened this month. The Kavli Prize for 2022 was given to 11 researchers, including Jacob Sagiv from Israel. Sagiv won the prize for nanoscience together with 3 researchers from United States. Their research is behind the surface technology that is used today in almost all parts of our everyday lives, from solar cells, batteries and printer inks to COVID and pregnancy tests, the Norwegian Minister for Research and Higher Education explained when he congratulated the winners earlier this month. I am pleased now to be joined by Jacob Sagiv, a professor of chemistry at Weizman Institute of Science. Hello, Jacob.
Hello, Conrad.
Shalom to you.
Shalom.
Thanks a lot for joining us. We were so thrilled when we saw this news, and my reaction was that we need to have this professor on for our live interview.
With pleasure. I am yours.
So. For our viewers that don't know you, maybe first tell a little bit about yourself.
About myself. I was born in Europe, actually, in Romania. And I arrived in Israel when I was 16 years old. This was in 1961, a long time ago.
Yeah.
And then I went to high school. I started this high school in Romania, but completed it here in Israel. Then I studied at the Hebrew University of Jerusalem, chemistry. And then I joined the Weizman Institute for my PhD work. After completing my PhD work, I moved to Germany. I was a postdoc in Göttingen at Max Planck Institute for Biophysical Chemistry with Professor Hans Kuhn, who was a leader at that time of work with what is known as Langmuir-Blodgett monolayers. So, and then at that time in Professor Kuhn's laboratory, I started the work for which is now recognized with this Kavli Prize.
Mm-hmm.
So all of it is about making very thin layers of molecules.
Mm-hmm.
You know, we are talking about layers. Now we refer to them as self-assembling or self-assembled monolayers, and I'll tell you a little bit what it's all about.
Yeah.
But we are talking about coatings, would say, of surfaces. You know,
Mm-hmm.
all materials terminate to the surface.
Mm-hmm.
So much of the properties of a material is determined by its surface.
Mm-hmm.
And the surface can be modified and engineered to display different properties by placing on it an extremely thin, ultra-thin layer, which is just 1 molecule thick. Now,
Mm-hmm.
we are talking about thickness of the order of 1 to about 3 nanometers. Now, a nanometer is 1 millionth of a millimeter.
Mm.
Okay? So
Wow.
This is the size we are talking. And not only that, a single molecule layer, a layer with the thickness of a single molecule can change completely the surface properties, but even you need less than a molecule. You can change only the top of the molecule. I mean, a molecule is made of atoms. So it is usually necessary to change only a little bit of the molecule, not its entire structure, to change completely the properties. And for example, we can have a piece of glass that clean glass, you know, it's wetted by water. If you put it in water, it come out wet.
Mm-hmm.
Just a layer of such molecules and will become phobic. It will become water repellent like a Teflon dish.
Mm-hmm.
So water will not stick to it. There are many other properties, of course, that I just give a simple example that everybody can, of course, understand what is going on. Now, what is all about self-assembling monoliths?
So just to be clear, so did you already in the 1980s develop like this coating that can repel water from, say, a glass of water?
Yes, of course. This is the simplest coating.
Yeah.
The simplest property you can get is that's why I am also mentioning it.
Yeah.
Of course, you can engineer the surface that it will adhere to it certain specific molecules, and then you can use it to sense those molecules, those materials. So this may become a sensor, which is a much more sophisticated, of course, application. In order to sense the molecules, you have also to couple that surface to an electronic device. So if you place molecules on a semiconducting surface, like silicon, we are all familiar with silicon devices. It can change the properties of silicon and turn it into a sensor for a particular type of molecules. So just example of, but I started this work at the end of 1975. And the first publications came from that laboratory. I mean, my publications in 1978. So between 78 and 80, this was the initial work that started this area of today nanoscience. At that time, we didn't know what is nanoscience. We did it without knowing what is it.
Yeah.
You know, this is many things in this world. You first do it, and then you put a label.
Yeah.
Okay.
But so this prize from Norway is a bit late in coming, you think, or?
It's about 40 years later, which, you know, I heard a colleague of mine here, also an old professor, who cited another old professor from Zurich, who said that you have to live a long life to receive awards. Of course. Sometimes there are inventions or discoveries that are pretty clear right from the beginning, but sometimes it takes time until the significance of what was discovered is realized.
And you write in you wrote a fascinating biography or autobiography on the KavliPrize.org website. I recommend all of the years to read it. And you write there in the end that today a self-assembled monolayer brings us on the verge of revealing the key to the holy grail of condensed matter physics.
Yes. Room
temperature, superconductivity.
Okay.
Are you able to explain that? Yes, even that for as an ignorant man as me?
Yes. Okay. I'm not okay. So this is now a collaboration project. I mean, we are the experts of modifying the surface and making the monolayers, changing the monolayers. Superconductivity, what is superconductivity? We all know that are materials that conduct electricity, copper wires. We all are familiar with this. But every electrical conductor has a resistance. We know when we pass electrical current, we generate heat. It means that there is a resistance to the motion. The current is, let's say, a motion of electrons inside the copper wire, but the motion is impeded. There is a resistance to that motion, and it generates energy which is wasted like heat. But under certain conditions, certain materials may be conducting without resistance. Resistantless, this is called superconductivity. Superconductivity is displayed by certain materials at extremely low temperatures, very close to what is called absolute zero. This is minus 273 degrees centigrade. So it's very low temperature. And we also know there are devices in which superconductivity is applied. For example, MRI instruments. MRI systems use very powerful electromagnets. So to generate the very high magnetic fields, you need a lot of current. Regular materials would melt under such conditions because of this resistance to generate heat. But using superconducting material, it's possible to pass current, extremely high currents, without resistance. But this again happens at very low temperatures, and this is one of the reasons that these MRI systems are so expensive. You have to conduct these experiments under very low temperatures. So you use for this liquid helium, for example. But there are theories that proposed again in the 70s that claim superconductivity should be possible also at high temperatures, at room temperature and even at higher temperatures. But this is not a matter of a certain material, but of an interface. And this is where we come into the play of the game. You have to generate an interface between two materials that has specific properties. And if these properties are met, the theory predicts that it should be possible to realize a superconducting interface. That means the current will not flow in the entire material, but just in a very thin layer at the interface, exactly a thin layer of the kind that we know how to make. So this is where we are at this moment. We can engineer layers that have this specific property. At the moment, we are not yet sure that we have superconductivity. This is something very, very, I would say, controversial. There were many claims of high temperature superconductivity that turned out to be false claims. So as scientists, you have to be very careful. You have observations. The observations suggest that we might have superconductivity, but we need a lot of additional work and very careful work, experiments that will unequivocally prove that this is the situation. So at the moment, it's just a promise. So we, as scientists, we always see something ahead of us. This is the promise, but then we have to prove it. And we have to be very careful. I mean, of course, we want very much to discover something new, but on the other hand, we always have to ask ourselves, is it true or this is fake news?
Yeah.
Okay. Yeah. So, you know, I always claim that a good scientist is a sort of schizophrenic person. You should believe in what you are doing, and you should always question yourself, perhaps this is not true.
Yeah, yeah.
Without belief, you cannot make any progress. And without proving that we are doing is true, you may reach false conclusions.
Yeah, yeah.
So here is where we are at the moment.
Yeah, it's fascinating.
And here we collaborate with a group of experts in superconductivity. These are physicists in the area of condensed matter physics. So they know how to detect superconductivity. I believe we know how to make it happen. So we have to join forces in order to find out whether this is true or not.
Yeah.
So there is still work ahead of us.
So are those researchers mainly based in the US or?
No. Here at the Weizman Institute, at the same institute, in our institute. It is very difficult to run such experiments across the ocean. So we prepare samples and we go to the instruments of those scientists and they measure what we are producing. So
all this, all the coating that you have helped develop for the last 4 or 5 decades, it's used on extremely many products, I gather.
Of course.
Yeah. I mean, so if you want to boycott Israel and you don't want the coating of the products, you have to leave it out.
I would prefer not to connect what we are doing with boycotts. You know,
no.
Science must be. Sure. Anyhow, what we are doing here at the Weizman Institute is primarily basic science.
Yeah.
I mean, we are not working on the applications. When I say that such a layer may be used as a sensor, we create the basic opportunities for somebody else who will take it over and create the sensor.
I see.
So there are, in science, there are a number of steps from the very basics to the very application, you know, when you are in an industrial product. So all these 4 decades, we have been working on advancing the basic know-how and capabilities of these layers and making more sophisticated layers. We started with 1 layer, now we can make multi-layers. This is like a multi-story building, where each story is a different molecule, for example. So there may be many, many different applications, and this is open for other scientists to take it further.
So you can't, the Weizman Institute and you yourself, you don't take patents on this, and we
take patents. We can take patents, but usually we take patents on the more basic aspects, not on the immediate applications.
Yeah.
I mean, this is not a rule, of course.
No, sure.
If you really are doing something that is immediately applicative, you can do it. Nobody will stop you.
Yeah. But I gathered from your biography that finding funding for the projects have not always been easy. I guess that's because one of the explanations for that is maybe that you do this like really foundational type of research.
Exactly. It is usually easier to get funding for something that is immediately applicative. For example, if you work on a vaccine. Just a example we are now aware of today. I mean, to make a vaccine, you need a lot of basic science. But the immediate funding you obtain is for the vaccine itself, not for the basic science behind the vaccine. So there are many people working for many years before those that make today the vaccine get the money, you know. So when you start with something new, you have to convince the funding agencies that this is worth funding. It is not easy if you cannot show an immediate application. I mean, we all know today that basic science should be funded. But which basic science? There are many new ideas. Many people propose many things, and how to divide the money between the different inventions and the different ideas, it's not an easy task, of course.
Sure. We have several viewers following this live stream congratulating you. They're saying, Anna says, Mazel Tov, Professor, for your amazing work in giving glory to the State of Israel.
Thank you.
And Hadass says Mazel Tov, and so we have viewers all over Scandinavia.
Hadass, I guess, is an Israeli.
Yeah, I guess so. She wrote it in Hebrew. So we have, and you came to Israel as a teenager. What has the country? What has the country meant to you throughout your life?
Look, when I arrived in Israel, the population of Israel was 2.2 million people. Today we are almost 10 million, I guess.
Yeah.
So it's a big change since that time.
Is it for the good or for the bad?
You always find good things and bad things.
Yeah.
We are always dreaming of the past times, you know. The life was easier. We could play on the streets. There were no cars. But everybody wanted to have a car at that time, of course, but not so many cars. Everyone wants to have a car, but he should be the only one driving it, you know. So you know, every advantage has also a disadvantage connected to it. Of course, our life today in Israel, in general, is much easier and better than it was 40 years ago. But there are aspects of the life that we would like to have them as it was at that time and not as it is now. I guess in Norway you are in the same situation.
Yeah, for sure. You wrote again in your autobiography at Kavli Prize, even these very days in Israel, we can exist only as long as we have an army that ensures our existence. You served in the IDF.
I served, yes.
And probably you have children and maybe grandchildren. Do you see a bright future for them in Israel?
We always hope. You know, the Jewish people survived with hope.
Yeah.
There are bad times. There are better times.
Mm-hmm.
Today, I think we are in a better situation than we were, let's say, 60 years ago.
Yeah.
But the bright future is still something that's not clear to me.
Yeah. No. Sure. That's probably in every country.
I don't know. We always claim that Scandinavia is the heaven compared to where we are. I don't know if this is your opinion about your country.
Maybe today, when we have almost 30 degrees and sunshine in the Oslo area.
Today?
But yeah.
So now we are in a better situation. It's not so hot here today. No.
Oh, okay. Yeah, but here in Norway we like to have it hot. But in Israel you look forward to more cooler climate.
Yeah, it's not so hot today here, by the way. So you win.
Nice. Yeah.
Today you win.
Today we win. What are you? Will you be coming to Norway to receive the prize, or have you already been?
I very much hope so. I don't know what is going on with this COVID. It goes on and off, on and off. Now they are talking again about restrictions, maybe.
Yeah.
But hopefully, I very much want to come, of course.
Yeah. What time is it?
It is at the beginning of, I think, between the 4th and the 9th of September. Is a week.
Yeah.
Kavli week.
And
it is a few days, I think, 3 days in Oslo and 2 days in Trondheim.
Oh, nice.
Yeah, yes, we were also going there.
Yeah. In Trondheim we have the technological university. Yeah.
And we are going to have a symposium there.
Nice.
Scientific symposium. Yes.
Have you been to Norway before?
Yes, 46 years ago.
Wow.
When I was a postdoc in Germany, in Göttingen,
mm-hmm.
I went with my car all the way from Göttingen to Denmark, Sweden, Norway, and back.
Wow.
So I think that the fjords the landscape of the fjords in Norway is one of the most spectacular landscape that I have ever experienced.
Yeah.
And I would like to come back and to have again that wonderful experience this time.
Yes.
Yes.
Yeah, and you will for sure see changes in the country as well. That's amazing. What will you use the prize money for? More research, or would you like to allow yourself some holiday?
I don't know yet. Frankly speaking, I have never received such an amount of money at once, so I have to make up my mind what to do with it.
Yeah.
But in fact, it's not so much. But if you consider what are the prices in Tel Aviv.
Yeah.
So with the money I receive, I cannot buy a room in Tel Aviv.
No.
in an apartment house, I mean.
Yeah.
So depending what you want to do with the money.
Yeah. In fact, one of our viewers say now that she is our board leader, or she's a leader of our local branch in Trondheim, actually. So she says maybe she invites you to stay one extra day in Trondheim to have to be a speaker in a MIFF meeting. So, but I can put her in touch with you.
Okay. We have not yet made. I mean, we want to take a few more days.
Yeah.
From Trondheim to for some sightseeing, of course, but we have not yet
Yep.
made any plans.
Yeah.
I'm going to come with my wife, who is also my research partner for the last 30, almost 40 years.
Yeah.
Okay, she was my first PhD student, and she,
Mm.
I think, is today the expert in this area of self-assembling monolayers in the world.
Mhm.
Okay, so we are going to come. She will join me, and also a son of us who is an architect. I mean, not molecular architect as we are, but a real architect.
Yeah.
And we want to do some sightseeing in Norway after this
Yeah.
lovely week.
Nice. That's wonderful. We will happily take you sightseeing too, she says. So
Okay, this is promising.
yeah. So Jacob, it was great to meet you. Thanks again. Mazel tov, congratulations with the prize. If you want to read more about Jacob's life, you can go to kavliprize.org, and you can hear about. But your life story I could understand, but the research things was a bit hard.
Okay, you have just to remember that every material terminates with the surface. And what happens on the surface, also on your surface, on your face, okay?
Yeah.
This influences what happens inside. This is the simplest message. So if you engineer what you have on the surface, you influence what happens also inside, under the surface.
Okay. So can you how can you give an example? Say if on the glass example that you used, will the molecules, will the material shift any character when you put the coating on?
This, I mean, in the example that I gave, what is changed is the wetting property. I mean, not the glass that is wetted by the way, also it became unwetted by oil. This is like a Teflon dish, it's the same property. So for example, I many years ago, I coated my windshield, my car windshield with such a monolayer, and went to Jerusalem on a rainy day, and I did not use the wisher. You know? So the stronger the rain, the better was the visibility of my windshield.
Wow.
So, but of course, this is just to show the possibility of an application.
Yeah. Yeah, we need that for our cars in Norway.
Yes. I think that there are Japanese cars that make such coatings today.
Yeah, probably. Again, Jacob, great to talk to you. Litraot, all the best. Have a good summer.
Thank you.
Yeah.
Have a
Bye-bye.
good summer too.